Recording start. Okay, maybe this is a good time to start. It's a pleasure today to have Michela Petrini, who will tell us about the supergravity duals of N=1 SCFTs.
Thanks a lot for the invitation. Okay, so backgrounds, the main concern of this talk will be ADS5 backgrounds in type 2B supergravity. And these kinds of backgrounds came to a renewed interest thanks to the SCFT correspondence, because as we all know, they describe the strong coupling regime of some CFTs. And a classical example is ADS5 times S5, who's the dual of N=4 supergamma in 4 dimensions. There is another class of dual pairs, which very nice properties, which are ADS5 solutions where internal manifold is a Sasaki-Einstein, which are dual to N=1 CFTs that live on D3 branes at the tip of a Calabi-Yau cone over the Sasaki-Einstein manifold. And in this case, the standard dictionary between geometry and CFT properties is even more developed. So, as always, global symmetries of the CFT correspond to isometries of the gravity dual. The protected operators are counted by cohomologies on the Sasaki-Einstein manifold, and the A maximization that gives us the R symmetry in the infrared correspond to volume minimization on the internal manifold that end up to be a Sasaki-Einstein. These solutions are nice, but maybe they're also nice because they are very simple in a way. Because the only non-trivial fields that we have are the metric and the 5-form flux, and they have isometries, which of course helped in finding the solutions. So the idea is to see whether we can say more about, something or study more general ADS5 solutions where the internal manifold is not necessarily Sasaki-Einstein and where all the fluxes are non-trivial. We already know some of these solutions, or solutions of this type, like Peach-Warner, or the beta deformations of the N=1 CFTs I mentioned before. But in general, these solutions are hard because, this is not the case of Peach-Warner and the beta deformations, which have isometries, and that's why we know them, because typically they have no global isometries. And so what I will do in this talk is to show that generalized geometry provides a nice framework to address, to study such backgrounds. And in particular, I will focus on the backgrounds which are dual to marginal deformations of N=1 CFTs. So in this talk, I will briefly recall what are marginal deformations on the CFT side. Then I will introduce the basic ideas we need of exceptional generalized geometry to describe such manifolds, such solutions, and then I will apply all the formalism, which I hope is not too heavy, to the specific case of marginal deformations of N=4 supergamma. And we will see that even if our original hopes to find the explicit solutions dual to these deformed CFTs failed, we couldn't find the full solution. But we can at least prove that such solution exists. And also we can find some sort of intermediate solution, which we will see why is enough to compute the Carroll rings and the index and whatever of these deformed CFTs. So the results I will discuss in this talk are based on papers I've written with Anthony Ashmore, Maxime Gabella, Mariana Gragna, Dan Waldram, and Ed Tasker. And also a lot of results are actually the result of the work of Ed during his PhD. Unfortunately, Ed died 2 years ago, and the results have been summarized in a paper which was written by Anthony and Dan. So let's start with a brief summary of what marginal deformations are, or better, exactly marginal deformations. So when we have a CFT, it is natural to see whether we can deform it in a continuous way, keep ending up always in other CFTs. This means that we need that the CFT admits exactly marginal deformations, which means deformations that respects conformal invariance also at the quantum level. When such a exactly marginal coupling exists, we say that the theory admits a conformal manifold. And for generic field theories, conformal manifolds are rare, and it's very easy to see why, because if we want another CFT, it means that we need a fixed point of the RG flow. So we have to find the zeros of all the beta functions of the deformed theory, and typically we have as many beta functions as couplings. And so if there are conformal points, they're isolated. The point is that things are different when supersymmetry comes in, and in particular for n equal to 1 CFTs, there are very nice results from Lee Strasser and Cole, and then Green, Komargowski, Tachikawa, and Weft that shows that exactly marginal deformations are quite generic. And so the way to find them is very easy. We start by looking at all possible classically marginal deformations. This means that we have to look for operators that we can add to our theory, and they come in two classes. One are superpotential deformations. This means that there are chiral superfields of conformal dimension 3, or a priori there could be also gauge coupling deformations, and this should be a chiral operator of dimension 4. It is actually quite easy to see that we can't have marginal deformations coming from gauge coupling deformations, because the only operators of dimension 2 are conserved currents, and so they do not deform the theory. So we start with our superpotential deformations, and then if the original CFT has no global symmetries other than the U1 R symmetry of n equal to 1, all the superpotential deformations that are marginal at the classical level, they are exactly marginal. On the contrary, if there are global symmetries which are broken by the deformation, typically these are the conserved currents that outside the CFT points, they're not conserved currents anymore. If this such a symmetry exists, then the exactly marginal deformations are a subspace of the classical ones, and this can be obtained as a quotient of all the classical marginal deformation by the complexified group that is broken by the deformation itself. To see why we have this very nice result, let's go back to the original what we're after, meaning the zeros of the beta functions for the superpotential couplings and the gauge coupling. And for n equal to 1 supersymmetry, these beta functions are proportional to linear combinations of the anomalous dimensions of the chiral fields. And when some of these anomalous dimensions are non-zero, we can see that in a way they are associated to an action of some global symmetries that act on the chiral fields, and these symmetries are the symmetries broken by the deformation. So the gammas are actually moment maps for the broken global symmetry group G. So if we have a moment map and this map acts on and then by the group G, and this group G acts on a Kähler manifold, which is the case for couplings of n equal 1 CFT, we can the solution of the moment map quotiented by the action of the group, because we want inequivalent deformations, will give a symplectic manifold, and this manifold is also equal to the quotient of all the deformations by the complexified gauge group. So once we have these exactly marginal deformations, one would like to study the theory, so see whether we can say something about the geometry of the conformal manifold, or we can count the chiral operators, determine the chiral ring and their relation, etc., etc. So let's see the prototypical example, which is n equal to 4 superior mills. We pick an n equal 1 supersymmetry. So in n equal 1 superfield, the field content of the theory can be arranged into 3 chiral superfields, which are in the adjoint of SUN and transform non-trivially under the part of the R symmetry which is manifest, so SU3R times U1R. And then we have the gauge superfield, which is uncharged under the R symmetry and still in the adjoint. The theory has a superpotential, which corresponds to an antisymmetric product of the three chiral superfield. So if we look at the F terms, in this case, the F term condition tells us that the fields commute. And so the chiral ring is simply given by all the symmetric polynomials in the scalars phi, in phi. So, now we can deform the theory, and a priori we can deform it by not imposing the relation between the gauge coupling tau and the superpotential H, which is enforced by n equal to 4. And we can also add an extra superpotential deformation, which is a symmetric product of the three chiral superfield, and so the coupling transforms in the 10 of SU3. So introducing this coupling breaks the global symmetry, the SU3 global symmetry, to a discrete subgroup, and we're only left with a continuous U1 R symmetry. So we can perform a standard one loop computation of the, let's say, in this case, a traceless part of the anomalous dimensions, which has this form. And this, we recognize here the moment map for the SU3 action on the space of coupling. And so we can compute the dimension of the conformal manifold, which will be the space will be given by the number of marginal deformations we can have, divided by the complexified SU3. So a priori we have this dimension. Actually, this singlet, which I isolated from the other, is just a possibility of moving the gauge coupling tau, which still has to be equal to H. This you see it from the n equal 1 algebra. And so these other two are the truly exactly marginal superpotential deformation. And if we use the SU3 symmetry to perform to rotate the chiral superfields, we can bring the superpotential in this form, where you see explicitly the two exactly marginal deformations. One is the beta function, known as the beta deformation, sorry, and the other one is a cubic. It's called the cubic deformation. If now we compute the F terms, the F terms now are non-trivial, and the fields now satisfy a non-commutative algebra, so the chiral ring relation will be more complicated. So now the idea is to see how we can translate this picture on the gravity side of the correspondence. And again, let me recall that I'm focusing in this talk on the n equal 1 CFTs that are on the work volume of the three brains at the tip of a Calabi-Yau cone of a Sasaki-Einstein manifold. So as I said before, the duals, which are known, correspond to type 2b backgrounds, where the metric is a work product of anti-de Sitter times the Sasaki-Einstein manifold. And the only non-trivial flux is very constrained, is S5, and it must be proportional. It's a sum of two terms, both proportional to the volume of anti-de Sitter and the volume of the Sasaki-Einstein. So if we now want to look for the solutions describing the deformed n equal 1 SCFTs, we expect them to still have an ADS factor because they're conformal. But because we also expect to have non-trivial dilaton, non-trivial Neves-Schwarz and Ramon fluxes, the internal geometry will not be the Sasaki-Einstein anymore. And also another thing that we expect is that the solution will generically not have extra continuous isometries rather than the R symmetry of the dual, the one dual to the R symmetry. So we don't know much about these dual solutions. There is a very nice class of solutions which are dual to the beta deformation of the supersymmetric field theory, and these are solutions, exact solutions of type 2b that were found performing duality along two U1 directions inside S2. And actually, one reason why these solutions were found is that they have extra isometries. They have these two extra U1 symmetries along which we perform the T-duality that's still there after the T-duality. And the same procedure can be extended from S5 to YPQ and in general toric Calabi-Yau manifolds. But if we want to look for the full set of marginal deformations, so for instance, for n equal to 4, both deformations H1 and the cubic one, then we are not in such a bad situation. The only known solution is the perturbative one by Aroni, Cole, and Yankelowitz. Perturbative, of course, in the dual of the deformation JK, and it's a second. It stops at third order, and the obstruction at third order gives the one loop beta function that I showed you before. So the reason why at the beginning we thought that using exceptional geometry could have been useful is that if you reinterpret the dual solution to the beta deformation in terms of generalized geometry, this T-duality action is very simple. It's simply the action by a bivector which appears naturally, we'll see later, in generalized geometry. So very naively we said, okay, we have many other objects on which we can act in general geometry. Maybe we can find the full solution dual to both marginal deformations. Actually, we couldn't, and we started a long time ago, but we couldn't find. But as I said before, we found some solution, we'll see in which sense, that is enough to extract some information about the n=1 theory. So in order to show you this solution, let me just recall briefly what is the exceptional generalized geometry that describes type 2B backgrounds with an ADS5 factor. So first of all, I think we all heard a lot of times by now, the idea of generalized geometry in general is to combine all the symmetries we have in type 2B in supergravity solutions. So in particular, the diffeomorphism and the gauge transformation of the potentials. For type 2B, this would be the two-form potentials, Ramon and Schwartz, and the four-form potential, and package them in a geometric thing, which we call generalized diffeomorphism. And the idea is that we can do that by replacing the tangent bundle to our manifold M5 to a larger bundle, which we call the exceptional tangent bundle, which locally is a sum of different bundles, the tangent bundle, the cotangent, and then all the exterior, and the forms with of odd degree, and the 5 form. And this extended bundle has a structure group, which is E66. And so this ordinary structure group of our M5 bundle is the geometric, let's say, part of this larger structure group. And these objects, the forms, they correspond to the charges of the object which we can put in our theory. So strings, branes, and kk-moves. So once we have our extended generalized bundle, we can build tensors. And in particular, to study the backgrounds dual to n=1 SCFTs, we need two type of tensors: the generalized vectors, so the sections of the generalized tangent bundle. And again, if I am a bit more explicit, this will be local sums of a vector, 2 1-forms, a 3-form, and a 5-form. And they transform in the 27 or 66. And then we need the adjoint bundle. Here you find the SL2 action of type 2B. This is the GL5 action here. These are the two forms which we can embed the Ramon and Neve-Schwartz potential of type 2B. This is the 4-form which we embed the 4-form potential. And then we have 2 bivectors, one of which we used to recover the beta deformation of Luni and Maldacena, and this is a 4-vector, and this can be obtained from the forms, just raising indices with the metric. This object is in the adjoint, so it transforms in the 78 of E66. So we said that we want to repackage our diffeomorphism and the shift of the potentials into a generalized diffeomorphism, which is generated by the generalization of the Lie derivative, which is the ordinary derivative, and then there is a bit which is the adjoint action of the extra pieces that we have in our generalized vector, which produces the gauge transformations of the potentials. How do we need to, in which way we need this tensor to describe our solutions? The idea is exactly what we have been doing for years, meaning that we can rephrase a supersymmetry in terms of G structures. And in this case, the idea is that we need some specific exceptional structure on our manifold. And the exceptional structure means that we have nowhere vanishing tensors that transform, that are singlet under some subgroup G of E66. And in particular, we need a generalized vector, which is then invariant and is stabilized by the subgroup F44 of E66 and must satisfy this sort of normalization condition. This is the cubic invariant of E6. And we call it, we'll see why, a V structure. And then we also need an element of the adjoint, but actually it's an element of the adjoint times some power of the volume. So that's why we call it a Wales as adjoint element. Again, it must satisfy some normalization condition, and it's stabilized by SU6. So it's an SU6 substructure. And this, I mean, will come. This is detail that might be useful for some of you who are more familiar with the story. Actually, this X defines a triplet of adjoint elements, because if I decompose into the real and imaginary part, I have the two adjoint elements that satisfy an SU2 algebra, so we have also a third element of the triplet. When these two structures are compatible, meaning that they satisfy some algebraic condition, they define a smaller structure, which is a USPC structure inside E66. So once we have this topological, the existence of these tensors, we can also impose some differential conditions, integrability conditions. The most natural one, and we will see that it's natural also from a physical point of view, is to ask, a very natural one, to ask that this HV structure, so have singlet intrinsic torsion. This means that the tensors K and X must satisfy some differential conditions. One is that K must have zero derivative with itself, that X must be of fixed charge under K, and then that K that J must satisfy these extra conditions. And these are moment maps for the actions of the generalized diffeomorphism on the space of this element X. And here LK is the Dorfman derivative along K. Sometimes, and we see why, one can impose a weaker condition where we do not impose these extra moment maps and we just impose these differential conditions. If we have this first set of conditions, we say that our structure is an exceptional Sasaki-Einstein structure. If we do not impose this extra bit, we say that this is an exception Sasaki structure. So how this is concretely realized, we can go back to the Sasaki-Einstein manifolds, which are dual to our n=1 SCFTs. Sasaki-Einstein geometries are SU2 structure manifolds. The SU2 structure is defined by a one form, a real two form, and a complex two form, and the rib vector, which is dual to the sixth form, the sigma, the one form. They must satisfy some compatibility conditions. These objects, they can be built if we look for if we think about our type 2B solution. The solution satisfies some supersymmetric conditions, and the SU2 structure tensors are built as bilinears of the Killing spinors on the internal manifold that satisfy this supersymmetric condition. And the supersymmetric conditions can be rephrased as differential conditions on the structure, which tells us that this structure must have singlet intrinsic torsion, meaning that whatever I do that when I take the differentials of the forms defining the structure, I end up in objects that are still singlets, so are still elements of the structure. So the standard SU2 structure in Sasaki-Einstein manifold embeds as an exceptional Sasaki-Einstein structure. The vector K contains the vector and the real form omega, while the X contains the holomorphic form. And then the C is the four-form potential of our solution. And if we impose on these objects these conditions, so the compatibility conditions and the differential conditions here, we recover exactly what we know, which are the SU2 structure conditions for the Sasaki-Einstein manifolds, which are equivalent to the n equal to 2 supersymmetry condition. So the reason why we go through all this generalization of the SU2 structure of the Sasaki-Einstein manifold is that we know now that if we want to describe a generic background which is dual to an n equal to 1 SCFT, so backgrounds with extra fluxes, not just the 5-form flux of the Sasaki-Einstein, these solutions are all exceptional Sasaki-Einstein. The idea is that, as I quickly said before, we take the Killing spinor satisfying the supersymmetric conditions of in type 2b. We split them according to the spinors on a DS5 and the spinors on the internal manifold, and this X and K can be built as tensor products of the n equal to 2 Killing spinors on M5. And one can prove that the supersymmetry equations of n equal to 2 supersymmetry, conditions of n equal to 2 supersymmetry are equivalent to these conditions I've written here. So can be rephrased as the fact that our HV structure that we build out of the spinors on the internal manifold must have singlet intrinsic torsion. So you see, it's really a parallel with what we know about Sasaki-Einstein. And exactly as we can do with the Sasaki-Einstein, the X and K can give us essentially all the physical field of the solution via a generalized metric. But I mean, we will not use this, and I will not deal more in that. So, but for one thing is that if we have this generalized metric, which contains all the fields of the solution, and we act with the derivative along K, we see that this is invariant. So this tells us that K is a generalized Killing vector. And actually, I mean, it's not a surprise, K contains the vector. This generates the isometry, which is dual to the R symmetry. So since we have all these formulas that allows us to enlarge the analysis of all, of solutions that are dual to more general n equal 1 SCFTs, we want to see whether we can find an exceptional Sasaki-Einstein structure, so meaning a K and an X that satisfies the conditions, the differential conditions I showed you before, that describe a marginally deformed n equal 1 CFTs. And if we find such K and X, how can we extract the information about the dual CFT? To do that, let me go back to the dictionary between ADS CFT and ADS and the gravity solutions, because I want to do the extra step to go to make the dictionary with our structures X and K. And the idea is that I can think about type 2b supergravity on an ADS 5 times S5 background as a 5-dimensional supergravity and n equal to 2 gauge supergravity with an infinite number of modes, infinite towers of modes. And these modes, I can organize them by splitting them according to the isometries of ADS 5 times, and then the internal part, I will organize it in representations of E66. And in particular, in doing that, what I have is that I rearrange the fields of type 2b supergravity according to the multiplets of n equal to 2 gauge supergravity. So the vector multiplets of the gauge supergravity will be given by the space of this V structure. So this global, because the idea is that I can think at the V structure along at all points of my manifold on my ADS 5 sorry, on M5. And similarly, the hypermultiplets correspond to the space of H structures. Then I can apply further the dictionary, which we all know and love, between n equal to 2 gauge supergravity and n equal 1 SCFTs. And we know the hypermultiplets correspond to current multiplets, short vector multiplets correspond to conserved currents, and long vector multiplets to semi-conserved currents. Once I have this, I can identify where the marginal deformations of the end of the CFT sits in my formalism. Because since I know that the marginal deformations are only deformations of the superpotential, which means chiral operators, I know that I have to look at hypermultiplets in the gauge supergravity. So for me, this will be X, the tensors in the adjoint. I know that there are no chiral deformations. I also know that if there are global currents, these global currents are broken by the deformation. This means that the currents are eaten, they become long multiplets, and these long multiplets in the supergravity are obtained by a Higgs mechanism where a vector multiplet eats an hypermultiplet. And in my language, the Higgsing means that actually what the Higgsing, the gauging, in gauge supergravity, this Higgsing is a gauging of the solution, and in my language, the gauging is realized by a generalized diffeomorphism. So my marginal deformations in my language, in my reformulation of supergravity, should correspond to the H structures modulo the equivalence class of generalized diffeomorphism, because all the solutions, because these are, I don't want the hypermultiplets that are Higgs to give the long multiplets. Okay, with this in mind, we can start looking for the solution. And we start from the exceptional Sasaki-Einstein structure describing our undeformed n equal 1 SCFT. And we look for a solution which will not change the K, because we don't have killer deformations, but we will change X because we add marginal deformations to the superpotential. So, sorry to repeat, what we find is that we can find a linearized solution. We can't exponentiate it, it's too hard because all the fields are turned on, but we can say something about the full solution. So let's first look at the linearized one. So as I said before, we start from our n equal solution dual to the n equal 1 undeformed SCFT, and we deform it. So we act with an element of E66. And the idea is that we want this to be still a solution. So we impose our moment map constraints and the Dorfman derivative, the conditions I showed you before, and this will fix for us, will tell us what is the deformation, realizing the marginal deformation. This procedure is exactly the analog of what Aroni, Cole, and Yankelowitz did in standard formalism of type 2b. What this way of rewriting, let's say, gives us more is that we can apply it to whatever Sasaki-Einstein manifold we have. And moreover, as I already showed here, this way of repackaging a type 2b supergravity gives a very nice parallel with a CFT. And so the way we'll see that the way we find the linearized analysis is really parallel to what happens on the CFT side. So when we impose the first part of the SUSY constraint, meaning the moment maps, what we end up is that all the deformations are parameterized by a holomorphic function of the Calabi-Yau cone, which I call F, and when the Sasaki-Einstein admitted a harmonic 114. And actually, we can really package these deformations in a way that is very close to the CFT. So these deformations are deformations of my H structure. So they correspond to hypermultiplets, so chiral multiplets in the CFT. And indeed, my deformations goes in doublets. And the one component will give the lowest component of the chiral superfield. So this is what will give waves and correspond to the chiral ring, while the other component will give the F-term component of the chiral superfield, so a superpotential deformation. And actually, we can be more precise. We can really look at how these linearized deformations are, and we see that we reconstruct the analysis. We find again the analysis of Igarashi-Tachikawa, where we find different types of hypermultiplet in n equal to 2 supergravity. One correspond to the trace of the chiral operators, which is a type of deformation. This one is the other possible type of deformation. This is typically what we have, for instance, on T11, where you can deform the difference of the two gauge couplings of the gauge superfields, and then we have some gauge couplings. So this solving just the moment maps gives us essentially all the chiral multiple of the theorem. Now we impose the other supersymmetric conditions, the LK conditions, and this fixes a slice in this big space of chiral operators, and tells us that of all the possible holomorphic functions on the cone, which actually we know give the chiral ring for n equal to 4, for instance, we select those that have weights free under the ring vector. So we select the marginal ones. And these are the classical marginal operators. If we want to exploit our formalism of exceptional geometry, all the essentially what are the classical what are these solutions? We can take the solution of a moment maps. These are all the chiral fields. We mod out by the generalized diffeomorphism that div k invariant, because we want our deformations to div k invariant, and this will give an hyperchiral space, which is a space of the chiral operator, the hypermultiplet. When we impose the LK condition, we fix a finite. This is infinite dimension. This is a finite dimensional space. These are the classical deformations. And if there are no global symmetries, we are done. These are also exceptional, exactly marginal deformations. When there are global symmetries, it means that the global symmetries are associated to some generalized vector realizing in the generalized diffeomorphism, which means that the Lie derivative of J and K are 0. And so in a way, some of the supersymmetric conditions we wanted to impose are not imposed because they are trivially 0. And to impose them, we have to do an extra quotient by the complexified group of these global symmetries that are broken. And so we end up exactly with the same construction that we have in the CFT, where the exactly marginal deformations are the quotient of the classical marginal one by the complexified group of broken global symmetries. So, for instance, if we take n equal 1 Supergian Mills as a Sasaki-Einstein manifold, this is a U1 bundle over CP2. We can parameterize this with the cone with 3 complex numbers. The condition that F must be holomorphic with 3 tells us that F must be cubic in this case. There are no other deformations because there are no 1-1 forms on CP2. And the obstruction, we have global symmetries, we know the SU3, so imposing this condition is exactly the vanishing of the beta function I showed you before, sorry, of the anomalous dimension I showed you before. And so we select out of the 10 classical marginal deformations, the 2 exactly marginal deformations. And if we compute explicitly, it's very heavy, so the X and K dual to the, corresponding to this deformation, and we compute the physical fields via the generalized metric, we reproduce exactly the solution of Aruni K, call A and K roots. So how can we go further and try to solve for the full solution? As I said before, exponentiating the linearized one, we spent a long time, we couldn't find any way to do it. And so after a while, after many tries, we decided to go by step. And so first, we can't find a solution of the exceptional César-Einstein condition. So we can't find the solution of the full set of supersymmetry equations, giving us a dual to an equal one CFT. But we can solve the simpler set of conditions, which I called before the exceptional Sasaki condition. So what we have in the big space of all the our fixed K and our X that we can deform, we find a line of a family of solutions. And then the idea is that if we wanted to see whether we can in some way go from this line family of solutions to the solutions of the full set of equations. So this red line is really, these are the solutions dual to the deformed and equal one CFTs. And the idea is that we can, and we see how, we can go from this to this by acting on our whatever point we find in this line of solutions by a complexification of a generalized diffeomorphism that leave K invariant because K doesn't change in the whole story. So the form of this family of solutions, let me call them X-ed for short, is very simple. So the idea is that you start from the original one. Well, for K, nothing happens, still stays the one of the dual of the undeformed solution. But the formed solution for X is very simple because essentially it's built in terms of the original Sasaki-Einstein quantities, so sigma, omega, whatever, and then just the function, the holomorphic function that determines the linearized deformation. And again, the expressions are not very illuminating. This is the action of two forms in the adjoint, which are linear in F, and these are these are scalars, not vectors, that are quadratic in F. And we can prove that the solution exists for any Sasaki-Einstein background. And again, if we specify it to S5, we reproduce, it's another way of reproducing the solution of Aroney called Yankelowitz. So if you look at this, you see that we have we can vary F. F is just a holomorphic function on the Calabi-Yau cone, so we can vary F. And so in this way, we find a continuous family of solutions. And the solutions, when F is very small, reduce to the linearized deformations. And what is important is these linearized deformations are solutions of the full set of equations. They're really solutions of this type 2D supergravity equations. So now,
can I ask a question there? How do I see smoothness of the solution? Or I mean, if you prove that the solution exists, how do I know that it's going to be smooth? Or is that built in? If it is built in, how do I see this?
It's built in. It's built in the fact that we built it out essentially out of these holomorphic functions.
Okay. Okay. Thank you.
So these are differential, these are continuous, so it's we can smoothly interpolate. So now the idea is that we want to find the full solution. So we have to impose the missing, let's say, SUSY equation, which I've rewritten this way. This is the mu3 moment map, but I've just rewritten this way and set it to 0, and we will see why. And again, the idea is that all these solutions, they form an infinite dimensional space, but on this space, we have a scalar metric. And this scalar metric is invariant under the diffeomorphism, the generalized diffeomorphism that leave K invariant. So this means that we can consider moment maps for this generalized diffeomorphism, this subset of generalized diffeomorphism. And the extra SUSY conditions, I can interpret this as a moment map for this subset of the GDIF. And if I'm in this setting, so we have a group which is GDIF K that acts that respects the Kähler structure, so respects also the symplectic structure on the manifold. We have a moment map. And so we can, and also, as I said before, these deformations are continuously related to the solution of the full equations. So we can continuously deform them close to the original point. So we are in the situation to apply a generalization of Kemptner's theorem, which tells us that there is an open set of stable points in this large space of solutions of our exception Sasaki solutions. So that's called them the XZ solutions that can be brought by an action of a complexified GDF K to intersect one of the points in the locus of this moment map. So this means that whenever which we can choose an XZ, provided that maybe we can't go very far in F, but if we keep F sufficiently small close to the original point, to the undeformed theory, to this XZ, we know that we can go applying a GDF to a solution of the full set of equations, so to a solution of dual to the marginally deformed n=1 CFT. And unfortunately, otherwise we would have the solutions to all dual to all marginally deformed n=1 CFT. We can't do it explicitly for a generic Sasaki-Einstein, but we can do it again for S5, or better, we can do it setting the deformation F just to the beta deformation of S5, and then we can find explicitly the GDF that takes us from the XZ solution for the beta deformation to the full solution dual to the that solves the equations, and which is the LM solution dual to the beta deformation. So this makes sense if we think at the dictionary between the CFT and our formalism, because we saw that the X's encode hypermultiplet deformations, encode chiral deformations of the CFT. So in a way, this XZ is a choice of the superpotential. And when I add the superpotential, a priori, we have a theory which is not superconformal. And then the superpotential in SUSY RG scheme do not change. And so when we go down from our deformed solution in the given superpotential given by XZ along the orbit of GDF K, what we're doing is that we have a renormalization of the Kähler potential. And with the renormalization of the Kähler potential, we end up on the new CFT, which is the fixed point of our RG flow. So not completely satisfactory, we don't have the solutions, but the point is that this partial solution, since this partial solution XZ contains all the information about the superpotential, because the GDF doesn't do anything on this class of objects, we can use XZ to extract the information about holomorphic quantities of the CFT. So in particular, we can see whether we can count chiral operators, and we can compute the Hilbert series of things like that. And the idea is that we can exactly as for Sasaki-Einstein, we have the transverse cohomology that were worked out by Gershmun and Tachikawa. The idea is that the counting of the chiral operator should be related to some cohomology, and this cohomology is determined by the set of all fields, all X, that solve our mu plus moment map, modulo the equivalence class under the GDF that leave K invariant. And what Ed proved is that indeed this is a new cohomology, and this cohomology can be graded by the charge under LK, which means on the CFT under the R charge. And I can also check that for ordinary Sasaki-Einstein, so no deformations, this cohomology reproduces the transverse cohomologies of the Sasaki-Einstein. And for the deformed Sasaki-Einstein manifold, essentially exactly as in the way we found the solution, all the non-trivial information is in this F function. And under the assumption that F doesn't vanish anywhere, it's possible to rewrite these solutions in this way, and then imposing the invariance under GDIF gives a cohomology which relates tensor product of forms in this way. And what's nice is that essentially it boils down, since the contribution from the deformation is in a way factor out, I don't know how to say, the computation boils down to using the Conrossi cohomologies of the original Sasaki-Einstein. This means that we can really compute, and this is what I did, really compute these cohomologies for a generic Sasaki-Einstein. So for instance, and then you can also compute the Hilbert series, so you can count your chiral operators modulo the F term and grade them by, count how many you have with a given fixed R charge. And again, Ed showed that the Hilbert series is related to the superconformal index, and modulo shift depending on the charges under K. And concretely, for instance, for S5, you can compute the Hilbert series for the undeformed solutions, and you find what was known for the Hilbert series. And for instance, here you have the operators of dimension 3, and you see that you have 10. These are the 10 classical marginal deformations. But you can also compute it for the fully deformed, not just the beta, the whole the two deformations of S5. And you have a new Hilbert series, where again, you see that now with R charge 3, you only have the two exact marginal deformations. And actually, this was already, this series was already computed by Van der Berg, associated to non-commutative Calabi-Yau algebras. Well, this is, unfortunately, this is not true only for the beta deformations, because in this case, this is a very specific, this is also related to the fact that you have these U1 isometries. This is a very specific case where the function F vanishes on the three lines of the cone. So it requires extra work to compute the cohomology. This I didn't write, but for instance, in Ed's paper, this same computation was done for the deformed T11. This is a new result that we couldn't find in math, and you couldn't do in standard with standard n=1 techniques. So let me conclude. The hope is that, I mean, general geometry is a very heavy formalism, but I hope I convey the message that in spite of this, it's a very useful tool to describe duals of superconformal theories, in particular n=1 CFTs, because this splitting into K and X really reflects the splitting into Kähler and chiral deformations, holomorphic and Kähler objects on the CFT. And this allowed us to prove that the dual of marginal deformation existed. I mean, one can say it doesn't really matter, but there were also some times ago discussions about whether such duals existed as standard geometries. Maybe they correspond to non-associative things. No, these are standard geometries, but simply we can't find them. But even if we can't find them, finding this partial solution, the X-Ed solution, gives us all the holomorphic information about the CFT. And so we can apply it to theories for which we don't have methods or easy methods on the CFT side. But we can also go further, because we know that there are many other interesting superconformal field theories. So for instance, we have other 4-dimensional n=1 CFTs that are realized on volume wrapped M5 branes, or we can consider 3-dimensional n=2 SCFTs in 2A. And what's interesting is that once you accept to consider exceptional groups, E66 for a type 2B on ADS5, or for M5 branes, wrapped M5 branes, or E77 in the case of 3D SCFTs, then you have really a unifying geometrical descriptions. The objects are exactly the same. They encode in the same way, holomorphic in the case of n=1 CFTs, holomorphic properties of the dual solutions. And so the hope is that we can really develop a formula that allows us to count protected operators and compute superconformal indices, and even find a very general description, geometrical description of A maximization, F maximization, and things like that. And this is, I mean, I'm very ignorant in this. It's something I really, I would like to study, because I think it would be very interesting. There are also nice link with geometry, so the geometric invariant theory, and also all the F term conditions of the deformed n=1 SCFTs that correspond to non-commutative Calabi-Yau algebra. So it would be interesting to see whether we can learn in this way things about these algebras and things like that. And I'm done. Thank you.
Thank you, Michela. Are there any questions?
I have a couple.
Go ahead.
Does this allow you to maybe learn something about the metric of the conformal manifold? Is there a way you could actually compute this?
Well, no. So to compute the metric, we need, in our language, we would need both K and X.
You would need them explicitly. So if you knew them explicitly.
Yeah, and we really need the solution. So for the beta deformation of n=4, we check that indeed we can compute this.
Okay.
But
what do you learn about the geometry of the conformal manifold? Is there anything?
We didn't study. We just checked that we could find the same result. But we in any case, our analysis is really close to the n=4 fixed point. But yeah, a priori, I mean, this was one of our motivation.
I see. So the moduli space of the theory should fiber over the conformal manifold. Is there a way you can tell me anything about that using this structure?
What do you mean?
So if I look at the moduli space of the theory, it should fiber over the conformal manifold, and that fibration can be non-trivial. So is there anything you could tell me?
What do you mean by the modular space? Isn't it the same as the conformal manifold?
Yeah.
Well, the conformal manifold is a space of exactly marginal deformations, right? But you can have moduli space, which is the space of vevs, for example.
But
I want to put the two together.
Yeah. So this we have. I mean, the space of vevs is counted by our cohomology, because this gives us the chiral operators, and the lowest component of the chiral operators are the vev. Yeah, this we can do.
Okay, good. So you can do you understand the fibration structure of this? I mean, it also should have interesting geometry.
To be honest, I never thought in terms of a fibration structure, but in a way.
Ibu, if it's described by cohomology, then there are standard things in algebraic geometry where you see a bundle of cohomology groups over a moduli space. There's probably some structure like that.
Good. So maybe it's computable. That would be interesting to get.
Higher derived functors is the technical term you want. I'm not sure you wanted to know that, but that's the.
I don't think I wanted to know that specifically, David. Although I should, right? But okay. But what you seem to be implying then, this might be computable from the data. So that would be interesting. I have one more question. Maybe I can have someone else can ask first. There's another question.
Well, let's see first if someone else has questions. I also have questions, but let's see if there are. I don't see any raised hands. Okay, go ahead. We will ask you a further question.
Okay, so a sort of curiosity in conformal field theory at low dimension with low rank, we expect to have, for example, theories with no marginal deformations, right? In a sense that are like very pure or seed theories. Is there any hope of maybe finding example of such a things with holographic duals, or could you actually prove that that could not happen?
Sorry, again, maybe low rank, you mean low rank of the gauge group, huh?
So if you have a, we know, well, actually doesn't, I mean, yeah, there are examples of theories which do not have marginal deformations. So in a sense, they're pure.
Well, here we are at large N because we have.
No, forget rank. He says rank because he has in mind the Coulomb branch. But,
yeah, I realize there is a language.
He comes from a different
translation.
He meant a few deformations.
Yeah, but yeah, a priori you can.
He wants to know if you can build this way theory without any conformal deformations, right?
Yeah.
Did I understand?
We should find theories. I mean, we take this. I mean, the cohomology is done by Ed. You look at cases where it's what corresponds here to the power 3 is empty, and then you have no marginal deformations. Whether whether you can realize it then on the geometry, one should try.
Okay, that would be
if you start giving mass to some stuff. I don't know how many. What are the deformations of Pete Warner, for example?
I think
Pete Warner, I think one or two.
Warner have deformations.
It is pure already, right?
Yeah.
So maybe you could. This is something I asked you already in some other occasion. Perhaps you could prove that there are analogs of Pete Warner for other theories.
I mean, it's not enough to say that if you turn on all deformations, that will do it, because you could float to a place where you can have new operators become light again, right?
Yeah.
So it's not enough. But this computing these cohomology groups seems to make. I mean, if you can tell me that there's the coefficient of the T cube is 0, that's where you have an example that's interesting. That is in some sense isolated, as close as you can get to saying you have an isolated ADS system. Yeah,
so I mean, one exercise we could try to do is, as you said, Alessandro, is to apply all this to Pilch Warner, which is a sort of a prototypical example of, and see.
And you can compute the Hilbert series with your methods in that case as well. I mean, nothing changes.
Okay, thanks. Thanks. I'm done.
Since you are on this slide, so the Vandenberg did this computation for the beta deformation, or do I misremember? What was the non-commutative algebra that he had in mind?
I don't remember. No, I think it was for the full one.
Ah, so for the generic one. So he had a reason of his own for considering the.
Because it's again, I'm very ignorant on that side, but I think it's one of the simplest non-commutative algebra you can study.
Okay, then even from a mathematical point of view, you get that. Yeah. Since I'm talking already, I'll ask one further question. So I think you can do the same for ADS4 as well, right? ADS4 in M theory.
Yeah.
I was curious if I think I asked you this in the past, but now I have a new question, which is, so I was curious if the description of ADS4 and theory vacua and the of ADS4 vacua in 2A with Romance mass if it's on the same footing, so to speak.
Yes,
almost if it's almost the same language, or if you have dramatic changes from one to the other.
well, the only change is that if you want massive 2A, you have to modify the Lie derivative, the generalized Lie derivative. So you deform it by a very precise term which we worked out that takes into account the Romance mass.
And this is a stuff that you did in the context of
Truncation.
Consistent truncations.
Yeah, but modulo that, and this is a nice deformation. So everything goes through, and you can apply it to both. And it is in that sense that I say that it's a very powerful unifying approach, because the logic is the same.
All right. I mean, from a traditional geometric point of view, for example, these two look very, very different.
Yeah, but also, for instance, the F maximization should be just in type 2B on 5-dimensional manifolds. The A charge is nothing else than what I showed here. Sorry, not even here, this. And for ADS4 backgrounds, the free energy is the analog given by the quartic invariant of itself. So in a way, once we understand what is the maximizing principle, it goes through. It's the same for.
The same. So, for example, the ADS4 in massive 2A, you would still call exceptional. Even if it's a 6-dimensional manifold.
Yeah, because the point is, depends on what are the conditions.
I mean, it's a little funny that you call it as exceptional Einstein, if it's even.
Well, let's say it's a solution that satisfies that correspond to a structure with which is a little more complicated, because when you go to 7 dimensions, you have an extra vector. You have 2 vectors, not just one here, but still you have some conditions imposed by generalized derivatives, some moment maps, and it tells you that you have a singlet intrusive torsion for this structure. So it's exactly the same.
Well, okay, I think I have some. There are several things that you could do then with this formalism and massive 2A. We should.
Yeah, we could discuss.
Yeah, we should discuss it. Further questions? I don't know if there are no further questions. Perhaps we can stop the recording.